Welcome to Red Dragon Mission Training. Your first mission, interpreting data. During this training mission, we will cover all of these learning targets. It's your job to master each of the learning targets to the best of your ability. Let's begin by talking about variables. Variables are any factor, characteristic, or condition that can be measured or counted. Variables fall into two categories. Independent variables. These are variables that you manipulate and control. The data that's plotted on the x-axis. So in a lab setting, this is the data that you are changing. Dependent variables. These are the variables that respond to the independent variable being manipulated. This is the data that you are measuring and that you're plotting on the y-axis. Let's try some examples. You let a toy car drive a distance of 1.5 meters and measure the time it travels. What is the independent variable? What is the dependent variable? Well, my independent variable is distance. I chose 1.5 meters. My dependent variable was dependent on how far I allowed that car to drive. I measured time, so it's my dependent variable. I would plot time, my dependent variable, on the y-axis, and distance, my independent variable, on the x-axis. On your own, use this lab information to find the independent and dependent variable. Variables have units and magnitude. The unit is any standard used for comparing measurements. What the magnitude of a value represents. So for example, distance is a variable that's measured in meters. Time is measured in seconds. Velocity is measured in meters per second. The magnitude is the size or extent of a measurement, the amount of each unit that is being represented. In simplest terms, it's the number. If I'm looking at 5 seconds, 5 is my magnitude, seconds is my unit. Negatives have special meaning in physics. In many cases, it has to do with whether an object is going forward or backwards. Let's look at all three of these terms, variables, units, and magnitude. A car is driving at a velocity of 23 meters per second. What is the variable? The variable is velocity. It's what we're measuring. What is the unit? The unit is meters per second. It's how much we're measuring. The magnitude is the amount. So I'm measuring 23 meters per second. That represents my variable, velocity. On your own, try this example. Find the variable, the unit, and the magnitude. Use this graph to continue to master the difference between independent variable and dependent variable. We record data in order to graph it and look for relationships. These relationships help us to quantify our world and take an observation and create a calculation. Different graph shapes give us different relationships. This graph is called a direct relationship. It's just a straight line. It's already straightened. If I were to linearize this graph, I don't need to do anything different to it. This graph we call a quadratic relationship. It's one of our exponential relationships and sometimes is called an upward facing or upward opening parabola. In order to straighten this, if I'm linearizing my data, I need to square all x values. So x squared is the key. This graph is called an inverse relationship. In order to straighten or linearize a graph like this, I need to invert all x values. So 1 divided by x. This relationship is a square root graph. This is also one of our exponential relationships, oftentimes called a sideways opening parabola. In order to straighten this graph, I'm going to square all of my y values, y squared. Linearizing our graphed relationships is the first step in quantifying physics. Once we have a linearized graph, we can start looking at the slope. If you're using a graphing program or a spreadsheet, the numeric or magnitude of the slope is often given to us. The unit isn't always given. In order to find the unit of the slope, you divide the unit on the y-axis by the unit on the y-axis. We know that slope is rise over run. Y is my rise, x is my run, so the y unit divided by the x unit. In order to define or explain the meaning of a slope in a particular graph, you need to use this general formula or format. For every x-axis unit, so whatever the unit on the x-axis is, the dependent variable increases by the magnitude of the slope and the unit of the dependent variable. So for example, if I was looking at a position versus time graph, for every second, which is the unit on my x-axis, the position, my dependent variable, increases by 4, the magnitude of my slope, meters, the unit of the dependent variable. In a graphing program, you may be given the magnitude of the slope, in this case 5. In order to determine the unit for the slope, I look at the unit for my dependent variable and the unit for my independent variable. My speed in this case, or my slope, is 5 meters, my dependent, per second, my independent. If I wanted to explain this slope relative to this graph, I could say that for every second, the position increases by 5 meters. The y-intercept goes hand in hand with the slope when we're trying to quantify an observation. The y-intercept is the point where our data crosses the y-axis, which is our dependent variable's axis. To find the unit of the y-intercept, look at the unit for the dependent variable. Since we're looking at where it crosses the dependent axis, we need to look at the dependent variable's unit. To describe the meaning of the y-intercept, use the following formula or format. It's always just the initial dependent variable of the object. So for example, the initial position of the object. It's the initial or starting dependent variable. Most graphing programs will give you your y-intercept's magnitude. In this case, 10. I need to find the unit of my y-intercept. I look at the unit of my dependent variable, in this case position. I know it's dependent because it's on the y-axis. So my y-intercept is 10 meters. To describe the meaning of this y-intercept, I would say that it is the initial position of the object. The slope and y-intercept often interact in a mathematical equation called slope-intercept form. Slope-intercept form describes the shape of a straight line. So once we've graphed our information, we need to try to write an equation in slope-intercept form. Slope-intercept form is y equals mx plus b. In this case, m is my slope, b is my y-intercept. In this case, all 4 variables will be replaced with values or the name of the variable represented on the axis. You will never have a y, m, x, or b in your final mathematical equation. This is unlike what you would normally see in an algebra class. Your y is not just going to be your y, it's going to be your dependent variable. Your m is your slope. This includes the unit. X is your independent variable, so whatever the name of that independent variable is, whether it's time, position, acceleration, whatever, that's your independent variable. And the y-intercept is your b with the proper units. Once we have our mathematical equation, we can start to generate a general equation. Mathematical equations represent just the data that we're looking at in our lab or experiment. General equations allow you to apply the observations in new situations. This is how formulas that we use in physics came about. We're going to use the units to replace all values with the appropriate variable. If a variable is already represented in the equation, we just drop it straight down. Let's look at the equation here, the mathematical equation. Position equals 1.5 meters per second times time plus 2 meters. All of my parts of my mathematical equation are there. Y equals mx plus b. I'm going to drop down all of my variables. So position is already a variable. It's going to stay position. 1.5 meters per second. That can't remain a number. Meters per second represents velocity. If there's a unit you don't know, you can represent that slope with just the letter k. Time is already a variable, so it comes straight down. Plus 2m, our y-intercept. Now again, the meaning of the y-intercept is the initial dependent variable. My dependent variable was position, so regardless of what unit I have on there, my y-intercept is the initial position. Notice that the general equation starts and ends talking about my dependent variable. Based on this graph, write a mathematical equation to represent this line. In order to create your mathematical equation, you just need to fill in y equals mx plus b. Y is whatever is represented on your y-axis, in this case, position. So y equals m. M is my slope. The magnitude of the slope is 5. The unit is meters per second because I take my dependent unit divided by my independent unit to get meters per second. That's just y equals m. I need y equals mx plus b. My x is what's ever represented on the x-axis, the variables, in this case, clock time. It's not the unit, it's not seconds, it's whatever's represented, time in this case. My y-intercept, because I have y equals mx, I need y equals mx plus b. So I find my magnitude of 10. It represents position, so I'm going to put meters, 10 meters. Now that you have the proper mathematical equation, try writing a general equation. The variables are going to stay the same. Position still equals position. 5 meters per second represents velocity, so I'm going to replace 5 meters per second with velocity. Variables remain variable, so clock time remains clock time. 10 meters, this is my initial position. Remember, the general equation starts and ends talking about the dependent variable. So we had position at the beginning of the equation, we have to have initial position at the end of the equation.